We're going to finish off section 2.2 on the derivatives of vector functions with two examples, example 2.2.3 and example 2.2.4. So the first example says that if we're given a vector curve, which is t squared times the vector 2 and 3t. So this is an example of a scalar function outside of the vector function. We're asked to find r prime of t in two ways. First way by multiplying in the scalar function, then differentiating. And the second by using a derivative rule. And then we're asked to check that both methods give the same answer. So let's start, first of all, by multiplying in. So r of t, if we multiply in, is going to give us 2t squared and 3t to the fifth. And so we can differentiate directly. R prime of t is 4t and 15t to the fourth. Next method, well, let's call the t squared outside a scalar function. Let's use alpha to match the notation of the previous video. So alpha of t is t squared, and let's call the vector part u of t, again to match the notation from the previous video, and that's the vector 2 and 3t cubed. So our vector function r of t can now be expressed as alpha of t times u of t, and our derivative r prime of t can be found using the product rule. Alpha prime of t u of t plus alpha of t times u prime of t. So alpha prime, if we take the derivative of alpha, we're going to get 2t times the vector 2, 3t cubed, plus alpha, so t squared, times the derivative of u of t. So the derivative of a constant 2 is 0, and then we get 9t squared. So we're asked to check that these answers are the same, so let's multiply through and add up. So we're getting 4t and 6t to the fourth, plus still 0 and 9t to the fourth. Add these together and 4t 15t to the fourth, which is exactly what we got using the first method. Example 2.2.4 is a little more theoretical. So let's read this and set up some notation. It says, show that if a differentiable vector function has constant magnitude, then the tangent vector is always perpendicular to the radial vector. All right, so let's let r of t be differentiable. And we are given then that our length is going to be some constant k. What we want to show is that the tangent vector, which is r prime of t, is perpendicular. So dotted with the radial vector, dotted with r of t, is equal to 0 for any t. And the way we're going to do that is by remembering this property, that the dot product of two vectors gives the length of the vector squared. So k squared is the length of r of t squared, which is r of t dotted with itself. Now if we take the derivative of both sides, the derivative of a constant is 0. Applying the product rule for the dot product, we get r prime of t dotted with r of t plus r of t dotted with r prime of t. Using the commutativity of the dot product, we can say that this is 2r prime of t dotted with r of t dividing by 2 on both sides, and we get our desired result. R prime of t dotted with r of t is equal to 0. Therefore, the tangent vector is perpendicular to the radial vector. So where have we seen something like this in real life? Well, a circle. So you imagine that you've got a radial vector r of t, and as the circle, or as t increases, the radius sweeps around in that direction. And we know that the tangent vector, the tangent is, so this is r prime of t. The radius, the radial vector, has constant magnitude. It does not change. And the tangent is always perpendicular to the radius.